Yes. So we will have a relation between focal length and radius of curvature in a curved mirror. We have seen what is focal length, what is radius. Every curved mirror is a part of a sphere. Suppose you take a concave mirror. Of course, you must be ready with your paper and a pen now. Take a paper and pen, start writing, right? Everything what I write, you have to write it. Because the gist of the derivation, this focal length and radius relation, we will write it and we will study the gist, right? All the things, sentences and other things you can join with them, join to the derivation later after looking into the notes or textbook, whatever it is. But the most part of the derivation must be studied along with the teaching. Okay? Be ready with pen and paper. Go and bring pen and paper. Don't watch this as if you are watching a film. No film heroes and heroines will come here. I am the only character you will, that you will see throughout the film. So have a pen, have a paper. Be ready. Correct? Right. Now, so we have a concave mirror. Its curvature is a part of a sphere. It will have a center. If you complete it, you will get the center. And if parallel rays are incident on the concave mirror, which are very close to the axis, after reflection they pass through the focus. In a concave mirror, they really pass through focus. They don't appear to diverge from that focus. They really pass through the focus. And this is the midpoint of the total area available of the area of the mirror, reflection area. That is the geometrical area. Its center is called pole. And you know the distance from the pole to focus is called focal length, and all the distances must be measured parallel to the principal axis. And distance from the center to the pole is called radius of curvature, R. Okay? Now, I'll take a parallel beam of light. Now, my job is to find out the relation between F and R. And in the beginning itself, I'll write what I am going to derive, F equal to R by 2. This is what we are going to derive. Every time when you study the derivation, you must know at the end where you have to reach, right? Simply keep on writing, don't keep on writing whatever you like and whatever you get, and finally don't underline whatever the answer you get. So you should get a particular answer. You must have it in mind that I have to get this answer at the end. This is the answer that we have to get at the end. Okay, so now I will rub it. I'll write somewhere here, F equal to R by 2. So focus is always at the center of the line joining center and pole. It should be at the middle. So this distance should be double this distance. F should be half of R. Okay, take one ray of light which is parallel to the principal axis, like this. Okay? Now, sir, any ray of light incident on any reflecting surface, if you want to measure the angle of incidence, you should have a help of normal. Angle between the normal and the incident ray is called angle of incidence. Sir, where is normal? Simply connect the center to this point. You will get a normal. So this is the normal drawn like this. It is a dotted line because it is not a ray of light. Okay, so this is the angle of incidence. I'll call it as theta. Theta is the angle of incidence. Okay, after reflection, you know very well with this. This is your friend now. Actually, the parallel ray of light incident parallel to the principal axis is your best friend. You know how does it move after reflection. What happens to that ray of light? So you keep on drawing this diagram as I draw this. Keep on drawing the diagram. Let your fingers know what is happening here and let it be recorded in the brain. So take a concave mirror and mark the principal axis. Geometric center is the pole, and you have a center here, that is the center of the full curvature, and this is the focus where parallel rays meet. Okay, and you mark the focal length and radius of curvature. Right? Are you ready? So shall we proceed? Okay. So this ray should get reflected at the same angle, because angle of incidence is equal to angle of reflection. So, and you know that you know very much about this ray. It should pass through the focus. And this is the angle of reflection. Angle of incidence is equal to angle of reflection, theta. So those two thetas must be same. So this is the normal drawn to this surface because it passes through the center, that's why it's a normal. And this is the angle between incident ray and normal. reflected ray and normal, we know that it gets reflected through the focus, and these both are thetas. That is over. Now you see here, this line is parallel to this line, because already we have announced that this is a paraxial ray which is parallel to the principal axis. This is a bisector. Now should I consider this angle as the alternate angle to this one, right, to this angle, because these two are parallel lines and this is a bisector and these two are alternate angles. What is this angle? 2 theta. So shall I write this as 2 theta? So this is 2 theta and this is 2 theta. Lines parallel here and a bisector. As I draw this, you two keep on listening and keep on writing the values, right? So a ray of light passes through the focus parallel to the principal axis initially, and this is 2 theta, angle of incidence, angle of reflection same. So these two are alternate angles, 2 theta, 2 theta. Okay. Now for this triangle, okay, I will name them. This is center, focus, and I will call this as M, ray of light hitting the point M on the mirror. So this ray hits the point M on the mirror and gets reflected. And I will drop a perpendicular from here. Okay, this is 2 theta. So I will drop a perpendicular from here and I will call this as D, MD. Of course, what about this DP? DP is negligibly small. If this ray is very, very close to the principal axis, if the situation is like this, if you have chosen a very ray which is very close to the principal axis, then if you had dropped a straight line here, perpendicular here, then this D and P would have overlapped. And as you take another ray which is very close to the principal axis, they come closer. So there is no gap between D and P. D is almost over P if the ray is paraxial, if it is very close to the principal axis. Okay, now you see this triangle CFM. In this triangle, this is theta, and this, I want to know what is this angle. If you know this angle, of course I can go for the derivation. These two angles are interior opposite angles to this angle. This is the exterior angle 2 theta, and for this 2 theta, these are the two interior opposite angles. Exterior angle is always equal to sum of the interior opposite angles, but this is 2 theta, this is theta, so this should be theta, right? Or you can argue it like this way also. These two are parallel lines, and this pink line, normal line to this surface passing through the center is a bisector. This is theta, this is theta. Alternate again. So for these two rays parallel, this line and this line parallel, pink line is a bisector. These two are alternate angles, so this theta must be equal to theta. Whereas this 2 theta is alternate angle completely to this one. So we have all the arrangements now. Theta, theta, and this is angle of incidence, reflection. This is alternate angle to this whole 2 theta. And for this theta, this is alternate angle with this pink line as a bisector, which is a normal line. Now if you want to derive this, search the triangles where these two things come, because finally you have to get a relation between them. F and R. See, radius is in this triangle, right? MCP or MCD. And where is this focal length? Focal length is in this triangle, MFP. So shall I take, and remember this situation is an exaggerated situation. Actually these rays are very close to the principal axis and they are moving like this, and they are making very, very small angles like this. That is the situation. Otherwise you can't trace them so easily, or you can't apply this derivation. The rays of light must be parallel to the principal axis and they must be very close. Then only they pass through the single focus. Otherwise they won't pass through the single focus. Okay. In such a situation, when theta, 2 theta, things are very small, you can go for tan theta. When theta is very small, tan theta is almost equal to theta, or tan I is almost equal to I. Tan x is almost equal to x. So now you take tan theta. What is tan theta here? In this triangle. Now I will search this triangle. triangle MCD. So in triangle MCD, right? In triangle MCD, and D and P are not much far away, they are very, very close. So you can take CD almost equal to CP. CD and CP are almost equal. This distance is not very large. Okay, tan theta in this triangle MCD, this is a right angle triangle because this is a normal drawn. So normal means this should make 90 degrees. Tan theta is opposite side. What is opposite side? MD divided by adjacent side, that is CD, right? So in the right angle triangle MCD, tan theta is, shall I mark it like this? So this is the triangle that I have considered, this one. So opposite side MD by adjacent side CD. Okay, now since when theta is very small and 2 theta, everything is very small, I can take tan theta almost equal to theta. So that implies when theta is small, hope you are writing this, write along with me, otherwise you won't be able to follow. Don't watch like as if you are watching a movie, simply follow this along with your paper. So when theta is very small, tan theta is almost equal to theta. So shall I write theta almost equal to MD by CD, equation 1. Similarly, go for 2 theta. You know what you have to get. R equal to 2F, F equal to R by 2. So keep it in mind always. When you study the derivations, you have to do like this. You should know what you are going to get finally. Then the derivation becomes easier. Otherwise, it will be stuck in the center, somewhere in between. You will not be knowing what to do, where you have to do, or what next you have to write. All these troubles will come into picture. Okay, now you want radius. This one. Take 2 theta. Tan 2 theta in the same triangle. So in the right angle triangle MFD, take tan 2 theta. Of course in this diagram 2 theta appear to be larger, but again I say this is a situation where the ray of light is very close to the principal axis. Then only all those rays which are close to the principal axis meet at a single focus. Tan 2 theta is almost equal to opposite side by adjacent side. Once again, tan 2 theta, opposite side MD divided by adjacent side FD. Tan 2 theta, MD by FD. But when theta is very small, 2 theta is also very small. When 2 theta is small or theta is small, we can write 2 theta almost equal to MD by, because tan 2 theta is almost equal to 2 theta MD by FT. Equation 2. Now, again, now from, if you want to compare these two equations, left hand side should be same, but this is 2 theta, this is only theta. So shall we multiply this equation 1 by 2? When you multiply this, you will get 2 here, 2 here. So you can compare the right hand side. So equation 1 multiplied by 2, what you will get? Equation 1 into 2 gives 2 theta almost equal to 2 MD by CD. Am I right? Now this is equation 3. Now comparing equations 2 and 3. Now it is purely mathematical. Comparing 2 and 3. Equations 2 and 3. What do we get? Left hand sides are same. So the right hand sides. MD by FD is equal to 2 MD by CD. Now MD can be written or it can be cancelled. What you will get? FD, invert this, invert on both the sides, or bring this CD by 2 here, FD here. So CD divided by 2 becomes FD, FD here, CD here, 2 here. CD by 2 is equal to FD, and you know that CD can be almost written as equal to CP. So because when the paraxial rays are incident, this ray is when very close to here, and this D and P are not much different, they are very close. So shall I write CD as almost equal to CP? CD is almost equal to CP. What about FD? FD is almost equal to FP. So CP by 2, FP by FP. Now what is CP? CP is nothing but radius of curvature. So CP is R by 2. What is FP? It's the distance from the pole to the focus, that is focal length. So this is a derivation. So F equal to R by 2. So always when you derive the things, you must be very careful. If you don't want to get stuck somewhere in between, sir, what to do in the next step? Usually in the examination, you will be under pressure because you will have to write all the things what you have studied throughout the year within 3 hours. And you will be having in mind that problem what I have read just 5 minutes back was tough. I have not answered it. Previous 1 mark question is pending and 2 marks question is not yet answered. Under all these pressures you have to derive this. It is not so easy. So you must know the step-by-step procedure. If you already have a target, what I have to get, then these steps become very easy. So once you know that you are going to prove either R by 2 is equal to F or R is equal to double the focal length, radius is double the focal length or focal length is half the radius. If you know that, after drawing this diagram, definitely you will come to know that you must take theta and you must take 2 theta because one double the other. And the best trigonometric function which will help you is tan theta, because radius and focal length come here and this will be the common. You see the beauty of the derivation. In both these triangles, one which I have drawn using yellow color and one which I am going to draw in green color. So you are going to take another triangle, you see, in the triangle MFD, see, green color, like this. In both the triangles, MD is common, which we are going to cancel later. And if MD is going to be cancelled later by taking common, that is opposite side, and FD and CD are all in the adjacent sides, it is tan theta which will help you. So if you have an algorithm like arrangement for the derivation, a diagram, theta, 2 thetas, all alternative and alternate angles, and then finally taking tan theta, tan 2 theta, and getting the equations, multiplying them by 2, finally arriving at this. So you should have a flow chart like this. What I have to do, what I have to get, what is the method followed, which is taken for help. Best is tan theta. This is common for both the equations, tan theta equations. One is tan theta, another is tan 2 theta. So these two will come in picture. So finally you will get radius is equal to 2F or F is equal to R by 2. So don't by heart it like a formula. Imagine always focus is at the center of center and pole. Focus is at the middle of center and pole. That means focal length is always half of the radius. So this is maybe a 3 marks question, very easy derivation. Obtain the relation between focal length and radius of curvature. But remember, this can be applied only for mirrors, not for lenses. Of course, you are going to study lenses. This doesn't help for lenses. This is only for mirrors. Now usually this question will be like this. Obtain the relation between focal length and radius of curvature of a mirror. It may be concave mirror or convex mirror. Or they may particularly mention you obtain the relation between focal length and radius of curvature using a concave mirror. Then this derivation holds good. And all the diagram here, when a ray of light falls parallel to the principal axis and all. But suppose you are asked to draw the diagram for a convex mirror and go for the derivation. Obtain the relation between focal length and radius of a convex mirror. So far it is not asked. They have not mentioned a particular ray diagram and they have not asked to derive it. They have asked you to derive it F equal to R by 2, that's all. So you can prefer this. Now suppose the same derivation using convex mirror. How can we do that? Derivation is as it is. No change even in the notations. Only the ray diagram is different. So you have to consider such a parallel ray of light passing through the focus at some angle of instance, and then you have to continue. Now let us draw the ray diagram. I don't do the derivation again because that derivation is same as this one. Now take a convex mirror. How to draw the ray diagram for the derivation of F equal to R by 2 or R equal to F using a convex mirror? Again, I take a convex mirror. See how do I take a convex mirror? I take it in such a way that I give an opportunity for the ray of light to travel from left to right, that is along positive x-axis. So this, I always follow this rule. Now this is the principal axis, this is the pole, but while drawing the center and the focus, remember, if parallel rays are incident on a convex mirror, they diverge in such a way that they appear to come from the focus here. Focus comes here and center will be somewhere here, because the curvature gets completed on this side. Center is here. Whereas in a concave mirror, it is, sorry, this is not the way, this is the way. For a concave mirror, center lies here, right, inside the mirror, whereas, center lies on the reflecting side. Here the center is not on the reflecting side, it is on the inner side. Okay, now, right, you have to consider a parallel ray of light. You remember what did we do in this diagram? We took, so this is the focus, this is the center, exactly at double distance. A ray of light incident along parallel to the principal axis passes through the focus. If you want to show that this angle of incidence is equal to angle of reflection, you have to draw a normal which is passing through the center. I and R are same, theta, theta. That's what we have considered. And we dropped MD perpendicular here, and this is the pole. Now we will do the same thing here. Take a ray of light, incident it parallel to the principal axis. Now after reflection, it should diverge in such a way that it should pass through the focus. Appear to diverge from the focus, not passing through the focus. So if this is the direction from the focus, this should diverge in such a way that it should appear to come from the focus, appear to diverge from the focus. So if I continue it like this, this will be the direction of the focus, so it will diverge like this. If it is a straight line, okay, this is proper, right. So any ray parallel to the principal axis after reflection will diverge in such a way that it appear to come from focus. Now, where do you indicate the angle of incidence and angle of reflection? Again, we have to go for the go with the help of normal. How do you draw a normal? Join the center, join towards the center like this. Continue this. So this is the normal line drawn at this point. Which is the angle of incidence? This one, theta. Angle of reflection, theta. So we have got this. So this part comes here. So again I will explain. A ray parallel to the principal axis diverges in such a way that it appears to come from focus. The diverging should be such that the first law of reflection should be obeyed. Angle of incidence equal to angle of reflection. So how do you get the angle of incidence and reflection? Just by drawing a normal, and normal line always is directed towards the center of the circular path, spherical part. Okay, now, so this is the direction towards the focus, and this is M, the point where ray is incident. This is a normal drawn to the principal axis MD. Now try to get theta and 2 theta. Now you see a straight line normal and reflected direction normal. This one proceeded here. This is theta. This should be theta. Correct? A straight line, a straight line. Vertically opposite angle, theta. And now suppose if I proceed this simply, for my understanding, like this, which I can write it as 2 theta. A straight line, a parallel straight line, and this is a bisector, correct? This one, reflected ray, is a bisector which passes, appear to come from focus. This is 2 theta. So shall I write this as 2 theta? Did you understand why it is 2 theta? A ray parallel to this one, these two are parallel lines. This is a bisector, a line passing through the focus is a bisector. This is 2 theta and this is 2 theta. They are adjacent angles. So this total 2 theta and this one, they are adjacent angles. So 2 parallel lines, and this is a bisector. Adjacent angles 2 theta, and if this is the exterior angle for this triangle, for this angle, this is the exterior angle. It should be the sum of the interior opposite angles. So this should be theta. Theta plus theta, exterior angle 2 theta. So this is the diagram. Once you go for this diagram, this is very much similar to this. Take the triangles MDF and MDC it is finished. And where is the focal length here? From the pole to the focus and from the pole to the center radius. So everything goes like this, but you must know how to draw the diagram for this, and everything goes in the same way. But usual asked question is using concave mirror, and if it is not mentioned, prefer concave mirror. If it is mentioned, of course, usually this will be asked, but better you be ready with this diagram also, so that if it is asked, same derivation holds good, because everything notation we have taken in the same way. Okay, you can just note it down how to draw this. Thank you. ಎಷ್ಟು ನಿಮಿಷ ಆಯಿತು?